Okay, in this video we're going to talk about the electric field that's created between two charged parallel plates. So what that looks like are two parallel conductive materials that are charged. So we connect this side up to the positive side of a battery, let's say, so it becomes positively charged. And we connect the other side here up to the negative side of the battery, and it becomes negatively charged. So we have two parallel conductive plates that are positively and negatively charged. So we know that there is an electric field created between these plates. And the electric field points then in this direction. And unlike the electric fields that we've discussed so far, what's unique about this electric field is that it's uniform. Okay? It always points in the same direction, and it always has the same magnitude. So this is our electric field. So we have a uniform electric field created between these parallel plates. Okay? And we know that the parallel plates are separated by a distance, let's say, of 1 meter. And we also know that there is a potential difference of 1 volt. Okay? So the difference in potential between one plate and the other plate is 1 volt. And what we get is a new equation then for the electric field between these parallel plates. And we take the potential difference and we divide by the distance. So what we end up with is a new unit for electric fields, which is volts per meter. And if you think back to a previous video when we compared electric fields and gravitational fields, we talked about how a gravitational field has two different units. We can talk about it in terms of the acceleration, which is meters per second squared, or the force per kilogram, newtons per kilogram. Same thing with electric fields. We can talk about newtons per coulomb, so the force on a charge, or we can talk about the potential difference between two plates separated by a distance. So again, we have two types of units for electric field, depending on what type of field we're looking at. So this electric field then is uniform, and if we imagine an electron in this field, we know that the electron will accelerate in this direction due to the field, right? It'll be attracted towards the positive plate. Okay. So the electric field then causes work to be done on that electron, and we know that the work is equal to the change in energy of this electron. And going back to previous equations, we know that the change in energy is the potential difference times the charge. So in this example again, we have a 1 volt potential difference, and we know the charge on the electron. So we know that the work done is 1.6 times 10 to the negative 19 joules. So that's a very tiny amount of energy. And in fact, rather than expressing the work or the energy in these tiny amounts in joules, we have another unit which we use, which is called the electron volt. And the electron volt is the amount of energy that an electron gains when it passes through 1 volt of potential difference. So this electron here that we've shown passing through 1 volt of potential difference gains 1 electron volt of energy, and that's an equivalent to 1.6 times 10 to the negative 19 joules of energy. Okay, so 1 electron volt is equal to this tiny amount of energy. So quite often physicists, when they're talking about the energy of subatomic particles or accelerators or things, they'll talk about the energy in terms of the electron volts, how many electron volts, rather than how many joules. because otherwise you'd end up talking about a tiny amount of energy because you're talking about a small particle. So the other thing that's interesting about this electron is we know that it's gaining energy. So we know that it's gaining, in this case, kinetic energy, and it's gaining 1.6 times 10 to the negative 19 joules of energy. So the kinetic energy gained by this electron, 1/2 mv squared, is equal to 1.6 times 10 to the negative 19 joules. And since we know the mass of the electron from our formula sheet, we find that this electron, when it passes through this parallel plate from one side to the other side, ends up traveling at 5.93 times 10 to the 5 meters per second. Okay, so I've taken this number, multiplied by 2, divide by the mass of the electron, take the square root, and you end up with the speed of the electron. So quite often in these parallel plate questions, that's what you're going to be asked. What is the energy gained by the electron, or what is the final velocity of the electron when it reaches this other side? So you're looking at finding how much energy does it gain and finding the speed from that energy, or maybe expressing the amount of energy in electron volts, which we would just divide the energy by 1.6 times 10 to the negative 19. Okay, so parallel plates actually appear quite often in everyday life. Most TV screens, old-fashioned TV screens, use parallel plates. The modern LED or plasma or LCD screens are slightly different, but the old-fashioned screens use something called a cathode ray tube. And this is a basic cathode ray tube. So this is the tube that was inside those types of TVs. It's also similar to what is set up inside fluorescent light. So the fluorescent light, again, will be similar to a cathode ray tube. So this is the screen of the television at this side. On the other side, we have two parallel plates. So there's one here which we call the cathode, and another one here called the anode. And the cathode is negatively charged, so electrons are attracted towards the anode, which is positively charged, and they travel in this direction then, just like they did in our previous example. So these electrons are being produced by the cathode, which is why we call it a cathode ray tube, and they get attracted towards this anode, which has a hole in the center, so it allows the electrons to pass through. So they're gaining energy in this section here. So this is the increase in the potential energy of or the kinetic energy of the electron as it travels through. And if we just left it alone, it would just travel in a straight line and it would end up here. And we don't want the electron to end up here. We want it to be able to scan across our whole TV screen, giving energy to the fluorescence on the screen so that it lights up and gives off colored light. So we need it to travel across the entire screen. So we use two more sets of parallel plates. These ones here are the horizontal plates. So again, if this plate here was a positive and this one was a negative, the electron would be attracted towards the positive plate, and the electron would steer towards this side of the screen. Okay, so rather than being at the center, it would steer to this side. And if we changed the sign, so made this one positive and this one negative, we could steer the electron beam to the other side. And the same thing over here. If this is the positive plate and this is the negative plate, the electron beam would be attracted upwards towards the positive, and you can see here they've already drawn that type of deflection. So these are the vertical plates, these are the horizontal plates. So again, quite often with these parallel plate types of questions, you may be given a diagram, a question with a cathode ray tube like this, and they might tell you the potential difference between one of these plates and asking you to find maybe the gain in energy of the electron, how fast is it traveling, once it's traveling through here, what's the force between the electron and the plates created by the electric field, anything that we've done previously. But that's a basic cathode ray tube. Basically electrons being generated, accelerated, and deflected by two different electric fields. And by varying the magnitude of the field, so increasing the potential difference or decreasing the potential difference, and changing the direction of the electric field, we can cause that electron beam to scan across the screen. And it does this incredibly fast, obviously because we need to have a very good picture on our TV screen. Okay, so that's basics of parallel plates. There's lots of good questions in the textbook for you to try. And as always, if you have any questions, you can ask me in class.